All right. So guys, the time is really yours. I can definitely speak to you up to 1 hour, or if we need to last a bit longer, that's also fine. So if you guys got any questions related to the contents for tomorrow, the written test one, maybe you can just let me know, right? I will just let you guys ask either on the chat or you can speak up either way. Go ahead.
Professor, I have a
Yes.
few questions in regards to I think the quiz that you have on
Yeah.
E-class.
The practice test. Yes, of course.
Yes, the
Let me just
practice
go
test.
there directly, and then I think it might be easier if I do the following. Okay, let me just go and then finish attempt so we can take a look. Okay. Yeah, Sarah, go ahead. Which question do you want to ask?
Oh, I want to ask about the first question. So it's saying for all x and y, x has to be a natural number so as y, where it implies that x times y is greater than 0.
Yes.
I chose the following, like the 5 and 4, the option, like it's a theorem and it's provable by 5 and 4, as well as the pair of 2 and 3. Yeah, the first, the second, and the
Okay.
fourth, and the fifth. But then it gave me just the one answer where it says the predicate is not a
Yeah.
theorem and can be disproved by 5 and
Yeah.
0, the
Yeah.
pair of 5 and
Okay.
0.
I see. So, okay, let's now take a look. So if you say that it's a universal quantification, you're basically saying that for all the combinations of x and y, they must satisfy this particular constraint. So if you want to prove it, you have to show that for every possible combination for x and y. So of course that'll be infinite because we know all the possible values for natural number will be infinite. So I would say usually if you got such a big range of combinations, it would be difficult. Well, it will be much harder to actually prove it. So it'll be much easier to disprove it. And the way you want to disprove it will be you want to find out one single combination where x is an actual number and y is a natural number. And then x and y would not be larger than 0. That means the negated version of this predicate. So let's take a
Yeah.
look at this predicate here before we look at the option you chose. If you look at this one here, we know that natural number will start with 0. That's a very special value you want to always remember. So let's say x and y, they are simply, they include a possibility of 0. So what if I just choose 0 and 0? Let's say, in that case, x multiplied by y is going to be 0. 0 is not equal to 0. So what I just described, like a x and y, 0 and 0, that's more like a witness combination for x and y to disprove this particular universal quantification. So that means the
Yeah.
whole predicate here is not a theorem. So
Yeah.
anything that has to do with the predicate is a theorem that should not be even chosen in the first place. So I would say 1 and 2, you definitely shouldn't choose it because
Okay,
it's not a theorem.
but then when you say in isolation, like consider each of the following statement in isolation, I thought that means like you just look at the statement and then you apply it to like the predicate. That's what I
Okay.
thought.
Okay. So, let's look at this. If you look at number 1 here, right? So we look at number 1 only. That's what I meant by isolation. So here it is true if you got 5 and 4 over here. 5 is a natural number, 4 is a natural number, and 5 times 4 larger than 0. I agree. But that one there is only one single combination. But to really prove universal quantification, you want to show for all the possible combinations for the x and y to really show that it's a theorem. So only showing one combination over here cannot be generalized into all the possible combinations. For example, if I got a combination 0 and 0, and suddenly 0 and 0 is not going to satisfy this, right? So if you think about the universal quantification itself, is really a predicate. The predicate will only be true if all the combinations of x and y will satisfy this predicate over here. If there's at least one predicate, at least one combination of x and y that's not going to satisfy this, then it's not a theorem. That's very important to understand first.
Okay, so basically what you're saying, since it's like a natural number, we need to have the combinations all the way to like infinity for it to be.
Conceptually, for natural number here, it's like an infinite set, which will go from 0 until plus infinity. That's conceptually. So that's why if you really want to prove somehow you want to argue that for all the values larger than or equal to 0, and another value that's also larger than or equal to 0, for all the possible combinations, they're always going to be larger than 0 when you multiply these two numbers together. But it's not the case always, because, for example, you can see 5 and 0 over here. This is not a valid. It's a combination where this property here cannot be satisfied. So that's why the entire universal quantification is not a theorem.
Oh, okay. And same thing with the second question, right? Because it's instead of the for all
Okay.
it exists.
Exist.
So then,
Yeah. So I think exist, the cases will be a little bit symmetric in the following sense. If you want to prove about the existential quantification is a theorem, it's much easier because you only want to show one witness combination. As long as you can find X and Y such that they are natural number, and then their product is actually larger than 0, I can easily find, for example, 5 and 2, let's say. In that case, this part over here will just be true. So that means the existential quantification is actually itself a theorem, because you just need one combination to prove it. So that's really the different natures about existential versus universal. That's really important to note.
oh, okay. Yeah, that makes sense. And can you also go over question 3?
Question 3 over here. Yeah, sure,
Yeah,
we can do that.
yeah.
Absolutely. So let me switch to my iPad over here. Okay, I think there's something going on, maybe some resource sharing on the chat. Let me monitor that maybe in a moment. So just to verify, but I'll do that in a moment. But now let me answer Sarah's question first, just to make sure. Okay, question 3. Okay, let me set it up, and then I will share my, I will switch to iPad. Give me a moment. Okay, good. Okay, let's now take a look. So we are basically, let me see this. Okay, so we got union, intersection, and also difference. I'm even telling you, what the syntax should be for the Roden notation. But for you guys, for tomorrow, as I clarified from today's announcement, so when you study for your test, you're encouraged to make some data sheets just to kind of summarize about what the math symbol should be and what the corresponding ASCII Roden symbol should be. But in the actual test, you will be expected to know about the symbols. Okay. All right, let's take a look at this.
Oh,
So
sorry,
we want to
Professor,
say
can we bring that sheet with us or no?
you cannot bring the sheets. That's my point.
Oh,
Because if you look at the
okay,
test
okay.
guide, under the rules, you're only allowed to bring the blank sketch paper. So that
Okay.
crib sheet I mentioned in the test guide is under the study section to say when you study, you can definitely prepare the sheet by yourself, but you cannot bring it to the test.
Okay, thank you.
Good. Okay, let's take a look. So here we are trying to calculate the cardinality, right? It's going to be some integer. And then the cardinality of the power set, right? If you remember the power set, that's how we write it, right? Back in the lecture. And in Roden, I believe is POW, but you can double check, okay? So this will be the set from which we want to take the power set, all right? So that's the one. Okay, let me write it down a little bit more larger. So we got A, B, C, and D, and set difference, A, E, and then union, A, F. And we want to take the entire expression over here. The entire expression, we want to take its power set. And then after that, we want to take its cardinality. So guys, this is the formulated version of the question, right? You can see this part here, I say the power set of, and then take its cardinality, which is over here, okay? But I think once we know about exactly what this set should be, it'll be much easier to calculate the cardinality of the power set, right? Let's do one thing at a time. So what about just this part over here? You can see this part here is calculating the set difference. Basically, we are finding all the elements that's in this set, but not in this set, right? So this will be, it will be B, C, and D. Agree? So B, C, and D are in this particular set, but none of them is in this set. That set contains only A and E. So we don't really include A in the resulting difference set. You want to check maybe the definition for the set difference. And then once we get this one here, we're going to take the union. So I'm going to say the union with AF. Right? So the overall is going to give us this resulting set. A, B, C, D, and then F. Right? So far, so good. And then we're going to take the power set of this. Okay? Let's say if I only ask you to really enumerate the power set, that's something we discussed in the lecture, right? But the question is about the cardinality, right? We actually spoke about two different formulas for you to calculate the cardinality, right? So I think this one here, we're not really restricting the particular set in the power set. For example, if you remember, what would be the power set for this particular set? It's going to be all the subsets of cardinality 0, all the sets of cardinality 1, all the sets of cardinality 2. So you should really know. If I ask you about, I'll just give you a side question over here. What about how many subsets in the power set of this are of cardinality, let's say 2? Right? So this is something that we spoke about before, right? So now if I want to, basically, this will be the largest set I can ever get. I want to take out 2 elements from there to make another subset. How many possible ways are there? In that case, I need to say 1, 2, 3, 4, 5. 5, choose 2. All right, so I think according to the formula, 5 times 4 divided by 2 factorial, which will be 10. That's about how many. Of course, if I didn't ask you to enumerate, that will be the formula you need to know, which we discussed in the class. But in the case where, yeah, sorry, Sarah, let me finish this, and then I'll take a question. Yeah.
Oh, okay.
So let's
It's
say,
number.
oh, not Sarah. Okay, and now just bear with me. So for this one here, if I didn't really ask you specific cardinality of certain subset, in that case, you basically want to think about each element has a binary decision, either to include it or not in the subset, right? So that means we got 2 to the power of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, which will be 32. So I believe that's the answer, right?
Yeah, that's the answer.
Okay, good. Okay, unless I was worried I might make some mistake. Anyway, so let me recap quickly, and I'll take some follow-up. So, guys, I think for tomorrow, you definitely these are simply some examples for you to really consider. So these are the set operations, and I think you definitely want to review. For example, what will be the symbol for partial function? What will be the symbol for what will be the symbol for total function? What will be the symbol for partial function, and etc. Right? You want to make sure you know them. And if I ask you any question like this, you ought to just compute based on this, right? There might be some relational image or maybe relational restriction, subtraction, and etc. And then to calculate the power set, I might either ask you maybe to enumerate exactly the contents of certain power set, or maybe I will ask you simply about the cardinality of the power set, or maybe I'll ask you more specifically about all the subset members in the power set. In that case, you can use the formula like that, right? Okay, please, question.
Yes. So I have 2 questions actually. So
Sure,
the
sure.
cardinality for the power set, is it 32 or is it 5?
It's 32. So
It's
here,
32.
think about this. We are taking the power set of a set that has cardinality 1, 2, 3, 4, 5. And the way to calculate the cardinality for the power set is to think about for each of the 5 members, we got 2 choices, either to include it or not to include it. So that will give us 2 to the power 5 combinations.
Okay. And then for to find out the subsets in a cardinality of 2, we do 5 times 4. Why do we choose 4 in particular?
Oh, okay. So here we got, to really calculate how many subsets are there of cardinality 2, we basically say out of the 5 members here in the set, we want to choose 2 members from there. For example, we might say we choose AB, we'll make it a subset, and then we choose maybe CD, make it another subset, and etc. How many ways are there for us to choose? So that'll be the formula. Let me try to remind you guys, right? If you got N, and then you want to choose N, just in general, it's going to be N factorial divided by N minus N factorial times N factorial. I think that's the formula. I kind of derived that very briefly back in the lecture. You can maybe check out. that part, but this will be the formula. Another way to think about it would be, let's say if I got 5 choose 2, it would be like a division. So 5 here, I'm going to go decreasingly. So 5 for 2 times, 5 decreasingly for 2 times, 5 times 4. Right? You can see I'm now having 2 terms, 1 and 2, which correspond to this. And then divided by this bottom component's factorial. Right? That's how you calculate. Yeah.
So if it's to find for cardinality 3, we have to do 5 times 4 times 3.
Yes, correct. I can write it down for.
Okay.
So if I say 5, okay, that's another interesting property. So 5 choose 3 would just be the same as 5 choose 2, right? So just for your information, if I say n, let's say this. If I got n choose m, it would be the same as n choose m minus n. It's just a property, okay? Sometimes you might find it useful. So now in this case, if you're supposed to calculate, let's say 5 choose 3, it might be just easier if you just find the other way, just 5 choose 2, but either way will be fine.
Okay, and so during the test, I understand that there's 10 possible relations in cardinality 2, for example. Do we have to list all 10 possibilities, or can
it
we list
depends
like
on
5
how the
of them?
question was asking. So maybe if the question say, just tell me how many there are. In that case, you just give me the number 10. If the question asks you to maybe numerate them, in that case, of course, you have to numerate all the subsets of cardinality 2. So it depends on what the question was asking. It depends.
Okay. All
Yeah.
right, thank you.
Okay.
Okay.
Professor, with that note, what you were just saying, can you please go, like, can you do like the 10 as an example? Because I was trying to do it and I was getting so confused.
You mean to get all the 10 subsets of cardinality 2?
Yeah.
Of course. Let's do that. Let's do that for sure. Okay, let me take this one here. Yeah, I can see that there were some questions over there on the chat. I'll try to answer. I'll get to you guys. Just bear with me. I'll just try to answer everybody's question today. Okay, so let me put it here. Okay, good. Let's say that is a power set. And we can even try to express it a little bit. So that might be a nice practice for set comprehension. So let's say we want to find the set of all subsets S such that S should be a member of the power set of A, B, C, D, and F. And cardinality of S should be equal to 2. This is basically something that we just discussed over here. Okay, so if you look at the set comprehension notation here, we're saying that the power set of some set is going to be a set of sets. And we're saying that S is just one of them, such that S is also has cardinality 2, right? That's what we're doing. And of course, I forgot some parentheses over here. And let's try that. So what we can do is, we know that there will be 10, okay? So we can say, let's try that. So we can do, let me see what might be the best way. Okay, so we basically just have to choose. It can be AB, okay, let me see what might be the best. Yeah, AB, and then AC, AD, and then AF. So far we have covered AB, AC, AD, and AF, right? And we can now start with B, okay? We can also try BC, and then BD, and then BF. So far, I have no repetition. So what after that we can do C, okay? So we can do CD, and then CF. Finally, I can start with D. It's going to be D and then F, right? It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 over here. Okay, I hope that helps for all the 10.
Yeah, that makes sense. Thank you so much.
Okay, very good. Yeah, so just in case, if I ask you to really enumerate, let's say a power set or as part of the power set like this, there might be certain rule to say you may have to sort, the elements in alphabetic order. So you just want to make sure you sort them accordingly. Okay. Okay, let me okay, M would be okay, some question about here. Okay, I'll just go in the reverse order. Let me handle some question on the chat. Okay, so for this formula here from Madison, so N here, yes, it's about how many elements we can choose from the set to make a subset. M here is about how many elements you want to choose from this set to make a set. For example, if you say 5 choose 2, we are saying that we got 1, 2, 3, 4, 5 elements over here for us to choose. And we're going to choose 2 of them to make a subset. So 2 of them here, 2 of them here, and 2 of them over here, and etc. All right. Let me take a look. You're welcome. Let me take a look. One question here about question number 4 in the quiz. Okay, let's take a look. Okay, so for question number 4, let me see. Okay, we want to convert the predicate to an equivalent one using the other logical quantifier, right? So let's see. Okay. You know, guys, just to save a little bit of time, I can maybe copy the answer as well, but I can rewrite it just to show you the process of thinking it. Okay. Let me set it up and then I'll go there. So that's question number 4. Okay, so let's now take a look. Right, so if you recall the rule from what we said in the class, if you got, let's say, for every, let's say, some x, and then you say range of x implies the property of x, right? So we said that it would be equivalent to, if you try double negation, not the case, there exists some x such that R of x and not px. And I believe we also even try to prove that a little bit, but let's not worry about the proof. Let's just try to apply. So you will need basically one negation over here and also one negation over here. Okay, and then of course you change the quantifier. So you see here we got universal, and in the answer we got existential. And then you can see we got one negation over here and also one negation here as well. However, this one here has already been simplified. Let me show to you. You can think about this part over here is like the P, right? This part here is like the P, but you want to get not the case P. So think about this one here. Let me go put it down here. So you're gonna say not the case x plus y larger than or equal to 10. Let me just use math form, and also x plus y less than 20, right? And we learned about De Morgan, right? Remember? So we can say not the case P and Q, right? Let me write it down. So De Morgan. Not the case P and Q is equivalent to not P or not Q, right? So this will be P, this will be Q. So you'll be not the case x plus y larger than or equal to 10, or not the case x plus y less than 20, right? You can see here, we already got the or, right? Used to be n, but after the negation, it become or. But how do we get this part into this, right? You say not the case larger than or equal to, that should be equivalent to strictly smaller than, right? I'm pretty sure you know that. So it be x plus y strictly less than 10, or, so now used to be less than, should be larger than or equal to after you take the negation. X plus y larger than or equal to 20. So that'll be the ultimate answer for this part over here, right? You got to do the simplification. Okay, so question here from Matthew. Would it be wrong if we don't simplify it on the test? Again, it depends on the test, right? So here you can see, since part of the question say relational expression should be simplified whenever possible. For example, you should write x larger than or equal to 20 rather than this. So that one is really a big hint about you should really simplify these two. So Matthew, I would say if somehow the question didn't really say this statement here, you don't need to simplify. Otherwise, you should. Right? It depends on what the question is. Okay. All right. I guess we got to go over another two parts of the question. I can do that. Just before I do that. Question 4, and there's some quiz to practice the event B to ASCII conversion. Okay, I haven't really seen that before, but I presume that's a valid one. And here from Ruth, not a theorem does not really mean axiom. So don't really get it confused. Axiom is really something that you assume to be true. You don't need to prove it. Theorem is like a predicate for which you have the proof or disproof its truthfulness. Okay.
Sorry, Professor, I have a quick question.
Yes, go ahead, please.
Yes, I have a question, one from the quiz.
Which one?
I just wanted the question 1 and 2 from the
1 and
quiz.
2? Okay, sure, go ahead.
I just want to know, like, how are you presuming that's a theorem and it's not a theorem?
Okay, so think about this predicate over here. So this predicate here, if you can prove that it's a theorem, that means this predicate here will evaluate to true. That's what it means. Let me put it this way. This predicate here actually tells you there are many different combinations for X and Y. Are they all satisfy this property? If it is the case, so that means this one universal quantification can be proved as a theorem. That's what it means. Does it make sense to you?
Yes, it does now. But when you said if I take 5, 4 as an example,
okay, sure, no
as
problem.
the pair, but it would say that the right side is also true and the left side is true.
Okay, very
right?
good. So think about 5, 4 over here. I agree with you. If you try to plug in the number for 5 and 4 over here, both of them are natural number. So antecedent is true. And also 5 and 4 over here for the consequent is also true. So true implies true is true. However, that true over there is only for a single combination for X and Y. In order for the universal quantification to be true, then we had to argue that every possible combination for X and Y should evaluate the true. Only showing a single pair evaluated true is not strong enough to show that it's always true. Right. If that makes sense.
Yes, but I just want to get a clarification. So if it was a negative number, say -5 and 4, the left side would be false, but false implies anything is true, right?
That's true. Again, so that's only just one combination, right? So here, universal quantification tells you want to consider all the possible combination that will actually satisfy this particular range. And for that particular example you just mentioned, let's say -5 and 4, that one there should not be so relevant because -5 is not going to satisfy this. You're right. The antecedent is going to be false. False implies anything.
Yeah.
So that one is not going to really show any progress to proving it because it will just be true. So whenever you want to show that, want to prove that a universal quantification is true, you want to argue that for every combination of X and Y that will make this true, it should be the case that this property is true. If you only show just one combination, it's not good enough. You want to argue for every combination. On the other hand, if you want to disprove, to prove that this universal quantification is false, you just need one witness pair to show that it's not always the case is true.
Okay, all right, thank you.
Okay, I hope that makes sense. Yeah. Okay.
Yeah.
All right. So observation over here. I'll get to the question here. Let me read the chat. The logic stuff is easy. I'm glad you feel that way. And the ASCII syntax that throws you off. I'm afraid that for this course, we try to, really try to combine both the logic in theory and also wrote in practice. So I'm afraid you need to know both. Okay. And final observation here before I take more questions. So natural number means that X and Y are larger than or equal to 0. Yes. That is why we cannot use 6 to disprove. Yes, that's right. That's right. If you look at option number 6, 12 and -2, -2 definitely is going to make this false because -2 is not a natural number. This combination over here is simply just going to make the implication trivially true. But to disprove it, you need something to make the implication false, right? All right, I can see Sarah also want me to go over questions 6 and 7. Okay. Any other question you guys want to speak up and ask? Otherwise, I'm going to go over 6 and 7 as well.
Oh, Professor,
Um,
could I ask something?
And then go ahead.
Yes. I couldn't raise my yeah, I couldn't find it. So yeah, basically, it's not about the quiz. So let's say for restriction,
Yes.
if we have a set, and if you're doing a relation restriction from relation R to relation to set S,
Mhm.
and we actually have more elements in set S that are not part of the domain of the R. So there are some extra elements
I
in
see what
S
you
that
mean.
are
Okay,
not
go ahead.
part.
Yeah, yeah.
Is it going to be like we ignore that, or is
Good
it going to
question.
be undefined?
Yeah. The question, the short answer would be you will ignore. Okay, let me give you one example. Let's say if you have a relation, and then I'll get to maybe question 6 and 7 as requested by Sarah. So let's say we have a relation here. Let's say we got A2 and also let's say B3. Make it very simple. So let's say we do a domain restriction, let's say. And then we're going to have, let's say, some very big set. Let's say we got A here, B here, C here, and D here. So Anthony, I believe that's kind of what you're asking, right?
Exactly.
Okay, very good. Okay, let's go back to the definition for, let's say, domain restriction, right? If I say I have some relation R, and then I want to domain restrict it to some set S. Okay, so that means I'm actually going to get another relation. Okay, so let's say X and Y, such that, first of all, X and Y should be in R, number one. So this is critical, right? And also, X should be a member of S. Okay, so you can see both should be true. Let's go one by one. Number one, so that's why I said the short answer will be you can just ignore in the following sense. If you fail this predicate here, that means the X should not be even included in the resulting relation. So now anything that's not really in, oh, sorry, let me say that again. So here we say that, let me start with this one here. This one tells you, you only consider the X and Y pair that's in this input relation. If there's anything that's not even there, you can just ignore. So only consider what's in R. Right? In this case, we got domain value A and B. And out of these two, which one are in S at the same time? In that case, it will be A and B, right? So that's why the resulting relation would just be basically the same. A2 and also B3 in this particular example. So, and then I hope that can answer your question.
Yes, thank you very much.
Okay, yeah, very good. Awesome. Okay. Okay, so all right, so I think I've been through the chat. Okay, let's now go over possibly 6 and 7. Okay, we still have time. If you guys got any follow-up that's relevant, feel free to put on the chat, or you can just speak up to interrupt me. That's okay. Why don't we take a look at 6 and 7? Okay, right, let's take a look at one by one. All right. For number 6, okay, let me just catch the entire thing. I'll set it up, and then I'm going to share my iPad in a moment. Okay, we can read the question together. Okay. So we got one set and second set, okay? And then we want to enumerate the following set over here. So this is a set comprehension notation. So we're saying that we're going to get the set of A and B, and what should be the constraint on A and B? A should be a member of S. B should be a member of T. And also A should not be X, and B should be less than 3, right? So let's see what's going on here. So that means A should not be X. So that means we don't consider Y. And B should be less than 3. So that means we don't consider 3. So here we only got the qualified value for A and B will be A could be X and B could be either 1 or 2. Right? So that means we're going to guess.
Sorry, Professor, don't we not consider X?
Absolutely. Sorry, I circled the wrong thing. Thank you so much. Let me do it again. Sorry for the confusion. So should be not equal to X. So we only don't consider X, only consider Y. And it should be less than 3. So we don't consider 3. Exactly. So what we consider would be the combination between Y and also 1, 2. So what we got is we're gonna have, so A and B combination here can be either Y1 or Y2. Okay, so what we got is over here, Y1 and also Y2. Well, that's exactly what you got over here.
Professor, so
Yes.
that sign where it says the slash equal, that means not equal?
Not equal to, yes. equal to.
Okay. If we don't know something like that, can we ask that during the test or?
Well, it's a tricky one. So because the test actually asks you to be familiar with the mathematical notation in ASCII syntax. So I would say I gave you some example already on the test guide. So I would say if you go back to lab 1, okay, I'll tell you guys what you can, if you want to do some last minute study, this is where you should go. Okay, you can take a look. So if you go back to, let me just go to E-class again. Okay, I'll show you where you can do some last minute study before tomorrow. So go to 3342 and go back to your lab number 1 instruction. And then under, I believe, resources, but let me double check. If you go to resources, okay, not here, give me a moment. I'll find it out for you. Okay, not here. There we go. If you go to page number 6, or back in your lab number 1 instruction, you will see that bullet point number 5. So this is an event B summary. Okay, hopefully many of you already explored that. If you haven't, still not too late. You still have some time to get familiar with it. So this part here is all the mathematical notation here on the left and the corresponding rodent syntax in ASCII on the right. Do you need to know all of them? I would say you only need to know those that we already covered in the math review lecture. For example, we definitely cover true and false. We cover conjunction. We cover this disjunction, and also we cover about set comprehension, right? And also we cover about union, intersection, and etc. Also, you will see some functional symbol as well. So I think this will be the part you want to study. And quantify union. That's not something we mentioned in the lecture, so you don't need to worry about this one here, right? Also, generalized intersection. Also, we didn't talk about it, so you don't need to worry about it. Okay. So I think, yeah, for these symbols here, I'm afraid. So for tomorrow, if you really call me for question about what this really means, unless it's really a typo I made on the question, otherwise I might say it's a part of the test. So I would say please get ready for the symbols for tomorrow. Okay. All right, so let me know. That's about 6. Okay, let me do number 7, and then I can see there are some new messages on the chat. I'll get there. All right. Let's now do number 7. All right. Again, that one seems to be more of the relational operation. You definitely want to make sure you're familiar with the relational operations. Okay. Okay, let me paste it. Okay, let's now take a look. So again, you got one set and the second set. And you have a relation here, which is a set of pair, 1, 2, 3, and 4. And this is what you want to do. All right. Now you want to really recall the notation over here. This one over here, and let me use a different color. And this one over here. All right. I'm pretty sure you guys know, right? This one here is really a range restriction. And this one over here, you can see that has an extra less than, so that means it's a subtraction, I believe, domain subtraction. So overall, this is what we have. We have the R, and you can see the parentheses over here. That means this one should be done first. So we want to do R range restricted to some set T, set difference too. We'll get there in a moment. And then after the result, we're going to get a domain subtraction. X. Right? That's of course, if you got a sketch paper, that's how you can convert, you know, from asking syntax into a mathematical symbol. Let's now try to evaluate just this part first, right? So you can see T is over here. So what will be is the set difference between 1, 2, 3, and 2. Everything that's in T, but not in 2. Basically got rid of 2. So that'll be 1 and also 3. Okay, it's this set. What will be the result if you want to do R range restricted to 1 and 3? That means you want to keep all the pairs where the range value is 1 and 3. This one here, this one here, and this one here, right? Let's now write it down. So this part over here, which will be the range restriction. This part over here, we're going to keep 1, 3, and 1, right? So it's going to be x1, x3, and also y1. And then we're going to apply this domain subtraction. So that means we're going to get rid of all the pairs where the domain value is actually x. So we got rid of these two. All right. So what we got ultimately will be after this will only be just y1. And I believe that's the answer. Okay. So Sarah, are you okay with this?
Yes, yes. Thank you so much.
No problem. Let me take a look. Okay. Let me see. Okay, how relevant is lab number 1 to the test tomorrow? Yeah, I think let's see. Will we be tested on specific things about the lab, like how to do an account transfer? Okay, I would say for lab number 1, you want to make sure you go over the solution and then make sure you understand how to do maybe, for example, relational overriding and how to do relational image, you know, etc. If there's really a particular event I want to ask you a question about, I'll make sure I give you enough context. But you want to make sure you understand the relational operator that's really used in the lab, right? That's something you want to make sure. All right, so I think Zachary is really recommending for that quiz. All right. Okay, I presume that one is very useful. Thank you. Do we need to know Maplet? Maplet, I presume you mean Maplet for relations, right? So no, I don't think you need. I think if you write a pair, right, for relation, I believe that's what you're referring to. This will be a pair, just comma. About will we be expected to know what a maplet is? I don't think so. The translation between account in lab 1 for maplet, you know, if you write a relation, it's going to be a set of pairs. So each individual pair will just be like this. So I don't think so. All right. Will the test question be significantly harder than the ones in the practice test? Well, as I said before, you know, you also saw that on your practice test. The practice test is only meant to give you the formats and some example question that might help you review. Your priority should be to review everything that we cover in the coverage that's listed in the test guide. Would that be significantly harder? It's up to individual person, right? To me, it's definitely harder than the practice test. But if you really study carefully about what we cover in the lecture, I'll tend to think you'll be fine. All right.
How many questions are there, Professor?
I haven't really finalized it yet, but since you guys got 40 minutes, I would tend to think I really don't know the exact number yet, but I think you guys will need to be very clear about the basic definition so that when you actually use your sketch paper, you don't really have to use too much time to recall what the definition should be. So you can just do some intermediate calculation so you can put down the result. And another question, another point I want to mention that might help. If you go back to your lecture slides, let's see about the math review, right? That's what we covered. And if you look at the table of contents, I'll show to you. Okay. All right. If you go to the table of contents, I think that there are at least two places. There might be more in case if that's the case, you can study more. You will see that there is one. Sorry, give me one moment. I'll find it out. Yes, there we go. You can see there is one slide about modeling decision, right? That's one. And then there's another one about modeling decision. You want to make sure you really understand the points that's being outlined over there. Basically, given some real life scenario, what should be the corresponding modeling decision that should be made, right? For example, should you actually make this particular mathematical object a partial function or a total function? That's something you want to be clear too. We also spend quite a bit of time discussing that in the lecture. Okay.
Professor, can you explain again the difference between a subset and a proper subset? I can't really point out the differences between them.
No problem. Yeah, sure. No
Thank
problem.
you.
Absolutely. So subset and also proper subset. I'll just give you an example and some intuition. I think for the formal definition, you can also refer to the slide, but let's just look at an example. Let's say if I have this. Let's say if I have, let's say S would be, let me give you STU. Let's say 1, 2, and 3. And also we got T here. Let's say 1 and 3. And let's have another one. Let's say for U here, let's say that's also 1, 2, and 3. Okay. Let's say for the subset, if I ask you about whether S is a subset of T, this one here should be false, right? It's not the case. Because in order to be a subset, every element in S should also be an element in T. But if you compare S and T, you can see 3 here is actually not in T, right? So for example, I'll put 3 here. So you'll see that's an example. On the other hand, if I try, let's say T, a subset of S, right? You can see I just change the order over here and to be T and S. So every element in T is also an element in S. Indeed, you can see 1 is here and also 3 is over here. So that's okay. All right. And then I can also try, let's say here, S is a subset of U for sure, because every element in S you can find its corresponding member in U. And actually they are equal. So that's why you can also get U is a subset of S. So all these are also correct. And let's try the subset, proper subset. Proper subset actually got one extra constraint. The left-hand side must be strictly smaller than the right-hand side. Let's try. So if I say S proper subset of T, by definition, it would be if and only if S should be a subset of T, first of all, and another extra constraint. Cardinality of S should be strictly smaller than the cardinality of T, right? So that's the formal definition. You can check. Okay, so based on this, so let's try. So S proper subset of T. You can see that one there already failed this constraint. So there's no way it's a proper subset. So that should be false. And if I say T is a proper subset of S, apparently this will satisfy this. But now is T cardinality strictly smaller than S? Indeed, you can see it's cardinality 2 to cardinality 3. So that one is okay. And let's get to S proper subset of U, right? So now you can see this one here satisfy the subset relation. But now is S cardinality strictly smaller than cardinality of U? No, they happen to be equal. So that's false. You can see it's failing this part over here. And similarly, if you got U proper subset of S, that's also false. So does it help about the two notions here?
Yes, yeah. So that's what made me confused. I was
No problem.
thinking if it's a
Yeah, actually, that's
subset,
very
how could it
important.
be a
Yeah.
proper subset as well?
Yeah.
Okay,
Another
so
another insight you want to really get is like this.
Mhm.
So let's say in general, if we got, let's say, if I tell you that S is a proper subset of U, you want to visualize this right away. Let's say S is a proper subset of U. That means there is at least one member over here that's actually in U, but not in S. A member of U, but it's not a member of S. Meanwhile, every member in S is a member of U. That one is really satisfying this relation. And the fact that you got at least one member in U, but not in S, that's really satisfying this, because T should be strictly larger than S as a set. So this diagram here is also something you want to think about too. Okay. So
Okay.
Wallet, yeah, sure. Wallet, you got some question, go ahead.
Oh, hello, Professor.
Hi.
Yeah, I have a quick question. So in the event B modeling summary sheet,
Yeah.
For the ordered pair, so in the
Yeah.
chat, there's two various ways to put, so I just wrote in the chat two various ways to put pairs. The
Let me,
event B modeling states that it's not the same thing. What exactly is the
do you know
difference?
which page it is so I can refer to it for everybody?
1 second. So it's in page, yeah, the first page, bottom
page.
right.
Bottom right.
It says that the ordered pair does not equal the EF between brackets. What exactly is the difference?
Okay. You know what? How about this? Let me look into this, but I think for now, for you guys, if you ever are asked to write a pair, that's what you're gonna write. Let's be consistent with what we cover in the lecture. You don't need to worry about this notation for tomorrow's test. I'll try to clarify on this maybe when we come back from the reading week. So that might take some time to actually explain, but let's not confuse you for tomorrow. So for tomorrow,
I
you
see.
only need to know
Because
this notation.
because in the solutions because in the lab solutions sheet, you use the ordered pair.
I use the order pair or like
on
this.
the
right?
left.
Okay, so I would say don't worry.
Yes.
So I think tomorrow, if you think where you really want to put a relation with the pair, you can always put comma. That's not a problem for tomorrow. And I'll try to explain about this one here after the reading week. I'll do that. I'll make a note myself. Yeah.
Okay. Thank you.
Sounds good. All right, guys. Any more questions? Yeah,
I have
yeah,
a
go ahead.
question.
Yes.
I was just wanting to confirm a partial function. When it's a partial function, it's talking in regards to like the domain, like if, for example, if you have like 1, 2, 3, right?
Yeah.
And then you have like a set of just 1, 2, that would be a partial function, right? Like we're not looking at the range side.
Yeah, you can think in this way. So if you say a relation R, let's say R is a member of maybe between S and T, let's say. And if you say that R satisfies the functional property, right? Whenever you have this assertion, you know, the functional property, you can definitely check back in your slide. That means every domain value can map to at most one value in the range, right? That's something we said in the lecture. Whenever you have this one, the case being the case, that means R is a partial function, no matter what. Partial function in some way is a more general concept, right? It's a partial function, always. And only certain partial functions can be a total function at the same time. And that's what you, like what you just said, right? And then I'll put down here. And then only those partial function whose domain is exactly the left set are total. So again, that's a very good example about proper subset, which one of you guys just asked me. So you can think about if I have, let's say this set here and this set over here. Think about this. Oh, you know, I'm pretty sure I drew this diagram in the lecture, so you can check. So this will be all the possible relations between S and T. Only those satisfying the functional property, they will be the set of all partial functions. And then only those that will satisfy the domain being able to being equal to the left set will be the total function. So that be total function. And of course, inside the total function, you may have other smaller, more special kinds of function, like injective function, surjective function, and etc. Right?
Okay,
Does-
and then
Go ahead.
sorry, go ahead. So for it to be like for a relation to be a function, it needs to have like a unique domain mapping to like at least one range, and the range can be like repeated, like it can be a duplicate number or whatever.
Yeah, I see
it
what
is,
you mean.
okay?
So for example, let's say here, let's say a total function over here. Let's say, just for example, let's say S is A and B, and T is 1, 2, and 3, let's say. Okay. So if you say total function, so that means, okay, function itself is just a relation. So it's a set of pairs. So to be total, so that means all the domain values should be there. Let's say A1 and also B2. Indeed, this is a total function, right? Because it covers A and B. Okay. And now this at the same time is also an injective function, because you can see A maps to 1, B maps to 2. You can see these two are different values. On the other hand, if I change this, for example, to B, let's say 1, this is still a total function because it still covers A and B. However, you can see A and B both map to 1. So this will make this total function not injective. Okay. Of course, you should definitely go back to the example that we talked about in the slides, and we got many examples there to show to you, the different categories of the function. So this is total, but not injective. Okay. So Sarah, does it help?
Yes, thank you so much.
Okay, very good, very good. All right, guys, any more questions? We still have 2 minutes, but I don't mind taking more if you got more questions. And then I can give you guys some final tips, maybe at the end. Okay, I can just pause a little bit longer. So maybe you guys maybe just a little bit more time to maybe review the stuff for tonight and maybe briefly tomorrow morning before the test. I'll give you guys some very quick tip, okay? Just in case it might help. Again, as I said before, you definitely want to be sure about modeling decisions, right? Here is one example, and also here is just another example, okay? And then you want to be sure you know how to really do proving or disproving quantification, right? So you can see this is one example here, right? Universal quantification. This is another one, existential quantification. And for propositions there, I want you to really be sure you know the definition for implication, okay? So if I show to you, let's say, give me a moment. Make sure you understand the truth table for implication very well. Over here. This part over here, okay? For example, true implies true will be true, things like that, right? You want to make sure you understand very well the definition for implication. I'm pretty sure you would need that for some question tomorrow. Okay.
Professor, would you ask us something about like how to say implication in different forms, like not
You mean
Q
this one here,
until
right?
P? Yeah.
Okay, so I think I don't quite remember if I put it. Let me try to be careful when I say that. All right, I would say, guys, I can give you I can tell you this one explicitly. For this slide particularly, you don't have to worry for tomorrow. For the various definition, you don't have to worry. But you want to be sure you know that when you come to the exam. All right. So for this slide specifically, you don't really need to memorize about the different ways to express the implication. But you want to make sure between now and the exam, you do take some time to really understand how to express each one of them. You may just want to go back to the actual lecture. I kind of try to go over each one of them by going over the truth table to see how you can understand each one of them. Okay. Be careful. All right. Any more questions? All right. Let me just monitor the chat for one more time, just in case I miss any question there. Okay, I do have something here. All right. Okay. You're welcome. All right, guys. If you guys have no more question, oh, wait. Okay. I'm glad somebody asked this question here. For tomorrow, please be sure you don't really go to the normal classroom for the test. You want to go to, guys, okay, you know what? I cannot emphasize this more, right? If you really go to the wrong place, nobody can save you, right? In case you don't know where you should really go, I'll show to you. But tomorrow, all right, if you look at the test guide, all right, look at here, and then you're going to Williams Small Center for the test. Don't go to the wrong place, please. All right. Can we bring a calculator? Yes. Although I don't really think you need it, but okay, guys, if you need you cannot use the calculator on your mobile phone. But if you want to bring a simple calculator, that's okay. Okay, that's fine. Guys, thank you so much. And then good luck to tomorrow. And then I'll see you tomorrow. Oh, take care. Bye-bye.
Thank you, Professor.
Bye-bye. Take care. Bye-bye.
Thank you, Professor.
Take care.